Hello, everyone, and welcome to today's webinar from Inorganic Ventures. My name is Brian Alexander. I'm the Chief Technical Officer here at IV, and on behalf of the entire IV team, we're very excited to have you with us today for the presentation on custom analyses by ICP-OES, with a focus on how to reduce interferences for 69 different elements. Before I introduce the speakers for today's presentation, we just want to talk a little bit about housekeeping, and particularly the question and answers period that we'll have at the end of the presentation. If you have any questions during the presentation, and we hope that you have lots of them, we would ask that you please type the questions into the Q&A feature. And then what we'll do is at the end of the presentation, we will read out and address all of your questions. And that Q&A session will be moderated by James King, our Director of Production. If you have any technical problems, please use the chat feature and send us a question about what issues you may be having. And Madeline Marshall, our marketing specialist, will be happy to help you with those technical problems. So with that, we'll go ahead and get started with our speaker introductions. We have two fantastic presenters for you today. Thomas Kozakowski is our Manager of Quality Control, and Thomas is a chemist with expertise in all things related to the manufacturing and testing of inorganic metal standards. He's also an expert in ICP and reagent synthesis and purification, as well as transpiration studies and research regarding container cleanliness. Our other presenter today is Mike Booth, who's our Director of Quality Control. Mike is also an ICP expert and is very knowledgeable with other analytical techniques such as ion chromatography and titration and wet chemistry applications. Mike has a Bachelor's of Science degree from West Virginia University Institute of Technology, and Thomas has a bachelor's degree in chemistry and also a bachelor's in forensic science from Virginia Commonwealth University. So those are your two presenters for today, and Thomas is going to go ahead and get us started. So Thomas, take us away.
All right, thank you, Brian. Welcome to our July webinar. We're going to go into some details on the method that we use here at IV routinely in QC for testing all the custom standards that you all purchase from us. So our key topics for today, we're going to go around some background information about our old QC method and what we have developed in the past year to test more and test better. We're going to identify the wanted improvements over the old method, and then we'll go through the process that we went through to create new calibration standards. And then we'll talk about managing spectral interferences, how we validated the method, and we'll go over the key benefits that we have gotten from, changing the method to our latest and greatest version. So as with all of our previous webinars this year, audience participation is encouraged. We're going to throw up some polling questions throughout the presentation to better understand our collective challenges. So these will be multiple choice. So when you get prompted, just click on your answer and we'll get to see the results from everyone. So make sure you're still awake. So we'll start off with our first question. What type of ICP-OES instrument do you use in your laboratory? So you might have Axial, only Radial. A dual view system would be choice C, where you have Axial and Radial capability on the same run. Or you might have an instrument where you can switch between Axial or Radial, but you have to turn the plasma off to do that. So we'll give you a couple of seconds to answer these. All right, that's exciting news. We are also very happy with our Axial and Radial dual view capability. So good to hear. So that is going to be the focus of this webinar. So hopefully you'll get some good takeaways from this. So we'll move into our background, what we used to do. So the purpose of our method in QC for routinely testing our customs, Inorganic Ventures manufactures over 10,000 custom blends per year. That's a lot. And our daily production range can go from 30 to 60 customs a day. And we really needed a method that could handle that high sample throughput but also be capable of guaranteeing the quality of our widely different samples. So I got a couple of examples of the kinds of blends that we have to test. These are some regular blends, some simple ones that are easy to test. So our IV Stock 3 solution is a 1000 ppm calcium, mag, potassium, sodium, all at the same concentration level. We're able to do a single prep to match with our high standard, and everything works well with just one dilution. Same thing with our IV ICP-MS 71A. It has many different elements, all at 10 ppm. So therefore we can again do a single prep to match everything to our high standard at 1 ppm. A little more complicated blend, our WWLFS1 ranges anywhere from 7.5 ppm silver to 1000 ppm potassium. So in this case, we actually have to run 2 different preps to stay within our calibration range. So our calibration range was 0 to 1 ppm. So our first prep here, we'll do 1000x. That lets potassium be on the high end, and we do capture calcium and lead at the low end. So those work very reliably. But the rest of them are below the calibration range, so we would really want to re-prep that at a different dilution to make sure those are within. So we do a smaller dilution at 100x, and the calcium and lead also get captured in this one at 1 ppm. And then silver is just outside of our calibration range, but that's okay because it has a very intense peak on 2 different lines, so that always works well. So our production workflow, like I said, it can range anywhere between 30 blends and 60 blends. We've noticed that, based on the types of customs that we get, our average preps required on a given day would be a pretty steady average of 1.5 per blend. So what that means is, the prep time at the bench for our technicians can range anywhere between 2 hours to almost 5 hours, which is a big change in time. So it's hard to keep them busy on certain days, but then they're too busy on other days. Another thing to keep in mind is the 2 positions you need on your auto sampler. So if we only have 30 blends, that occupies 45 spots, no problem. But if we have 60 blends, we get 90 samples. That actually doesn't fit on the auto sampler because it can only hold 84 tubes. These are those 50 mil centrifuge tubes that you can buy. Work really well for prepping. They stand up on their own, relatively clean, and work very well. I did want to point out, though, that with instrument time, we don't really care. We prep our samples throughout the workday, and then at the end of the day, we'll start our run, and it will automatically shut off when it's complete. So we don't really have to worry about that because it never goes beyond about 4 or 5 hours. So it shuts off sometime around midnight, and then we clean the instrument the next day. So our old custom blend method, like I said, had 3 calibration standards, and they happen to be in 10% HCl, which does make silver photosensitive. So that's one of those limitations that we had to deal with. But the blank solution is just 10% HCl. And then our low standard is 0.1 ppm, and the high standard at 1 ppm. We did include the use of a ionization buffer. So all of our samples and our preps, standards, all of it gets 500 ppm cesium added to it. And this helped with the signal response for lithium, sodium, and potassium. Like I said, though, you need to actually add this to all the samples and the standards so that you get consistent results between all the intensities. Overall, this method tested 67 elements, and we only used axial mode for this method. That's why we used the ionization buffer. With all the standards present in the standard, some lines have major interferences, making it difficult to use those ideal lines that are out there. So next, we're going to identify the wanted improvements. So I'm going to pass this over to Mike.
Thank you, Thomas. Yeah, this section of the presentation, we just wanted to review, you've got sort of a more detailed picture of what our old method was. There was room for improvement. So the first step was just to identify what we wanted to improve. And based on the slides that Thomas had just shown you, we came up with these 4 sort of hard improvements that we wanted. The first was to decrease the number of preps required per sample. So just a reminder, it was 1.5 preps per sample with the old method. So we wanted to cut that down as much as possible to one, allow us to run more samples if we needed to go above 60 per day. Wouldn't run into any issues with the auto sampler. And two, sort of get a more consistent prep time for our QC technicians at the bench, ranging from 2.5 to 4.5 hours. Can make for an interesting work day to day. So we wanted to try to level that out as much as possible. So how are we going to do that? Our idea was to expand the calibration curve. So increase the number of calibration solutions and increase the concentration of the high standard. Our old high standard was 1 ppm, which you saw in the previous examples meant that we had to do a lot of dilutions to dilute down to that amount. But if you increase the overall concentration, one of the things you're going to run into is you're going to go over range for some emission lines as you increase concentration. So what we wanted to do was take advantage of our radial view to avoid going over range for certain elements. The second improvement that we wanted was to add rubidium and osmium. Now, rubidium and osmium are not the most popular elements to be added to solutions, but they do come through, and we like to try to test everything we can with as high quality as we can. So instead of pulling any blends with rubidium and osmium off to the side and then doing maybe like a separate ICP mass spec check or some other type of just different run other than our normal daily run, we wanted to include those elements in so we wouldn't have to go back and essentially double check blends just to get rubidium and osmium. So what we did was we wanted to add those to the calibration curves, and Thomas will go over how we added rubidium and osmium in the next section. The third improvement is to decrease the amount of time required for each sample prep. So again, 1.5 preps per sample. On average, our technicians were taking about 3 minutes to prep each sample. So that's where the math came from to figure out how long prep time was. So if we could cut that amount of time down, we could essentially allow ourselves to do more samples per day. So how are we going to do that? We're going to remove the cesium ionization buffer. As Thomas mentioned, cesium ionization buffer was added to everything, the calibration standards and the samples. So what we were doing before was aliquoting our sample and then spiking cesium into it. So if we eliminate that spiking step, it should save us some time. And we're also wanted to change the default prep volume. Our old default prep volume was anywhere from 20 to 50 mils to fit in those 50 mil centrifuge tubes. We wanted to switch down to 10 mils. And part of the reason we were able to do this is if we expanded the calibration curve, we could ensure that we wouldn't have to dilute as far and maintain large enough sample aliquots so that we weren't trying to aliquot, microliters. We could stick to the milliliter range to get good weights on our sample aliquots. And the fourth improvement is we wanted to decrease the amount of corrosion on the instrument. So our old matrix was 10% HCl. So if you can imagine, these instrument run times were anywhere in the realm of 2 to 4 hours, depending on how many samples we had. That was 5 days a week, every day, along with any sort of, if we were really busy, we might do what we would call a mini run during the day. So that's just more time that you're running 10% HCl through the instrument, and 10% HCl can corrode the torch box. So this picture is the torch box of our old workhorse ICP-OES, and you can see there's a ton of corrosion on everything from just the overall box to the RF coil, the plasma interface. So we wanted to eliminate as much HCl as possible to cut down on that corrosion. So we have a second question for y'all. Of those 4 improvements, what would be at the top of your most wanted list? All right, and we'll wait for the results to come back. Okay, so yeah, this is pretty much, the decrease the number of preps and decrease the amount of time. Those were key factors for us as well. Yeah, this fits in line with pretty much our thought process. So with that, we're going to jump over to the next section, and Thomas is going to take over once again.
All right, thanks, Mike. Our next section, we're going to talk about creating the calibration standards for our new method. So this is all of our method development activities to get to where we are today. So we wanted to split the calibration standards. So I don't know if you've watched some of our previous webinars, but when I talk about what we do for trace metals here at IV, I have 2 sets of standards for that method, and that was mostly for chemical compatibility. So the way we wanted to split them up for various reasons. So one, chemical compatibility, certain elements don't behave well with other elements. It's usually due to chemical form, but also matrix. So in the case of barium, I mean, if you add a sulfur that's in the form of a sulfate, you'll precipitate barium sulfate. It won't go back into solution. You'll have a clogged nebulizer and all kinds of other problems. Other elements have different kinds of chemical issues with others. So we want to keep those separate. The next is matrix compatibility. Some elements precipitate in the presence of HCl or HF, but as you all know, certain elements require HCl or HF in order to remain stable. So we wanted to split those up in order to satisfy matrix requirements. And finally, we also wanted to split them up for spectral reasons. There are a lot of interferences out there that interfere on the major lines, the ones that the instrument software says, hey, this is your ideal line. Well, if you have this other element, it might not be the ideal line anymore. So we wanted to try to mitigate that and still utilize some of those good lines to get high quality data. And of course, that can happen with any element regardless of the matrix. So that's all has to do with the chemistry behind the electrons and how they behave in the plasma. So this slide kind of shows all the elements in our method. So basically everything in white is in our old method. And as you can see, all the elements are okay at 1 ppm. So this is a concentration that actually works, even though we have some HF and HCl. No problems at 1 ppm. Basically, they would precipitate at higher levels, but 1 ppm seems to be our gold standard. If you go beyond that, we start to see problems with certain elements first and other ones later. But as we mentioned, we really wanted to expand this calibration range much higher than 1 ppm. So at 50 ppm, we run into some problems. So everything in red, is an element that we've identified that would definitely precipitate based on our stability over the years, things that we've quoted for customers that ended up not working. There are a lot of different things going on here, and I've detailed that on the next slide, but just looking at this one, we can see you wouldn't think potassium would have any issues, but believe it or not, at high levels with silicon, it can form a gel in your solution and actually stick to the walls of your container. Cesium and rubidium, you also wouldn't expect to see issues, but when you have HCl and platinum involved, you actually create an insoluble cesium hexachloroplatinate. We've actually had this problem all along with our old method. We add cesium to everything. So whenever we had platinum involved, we would actually get better results if we did not add the cesium buffer to the prep. So that was, and one of those instances where we had to do a deviation from our method in order to get something to work. We wanted to get rid of that. Obviously, a major one is HF with all the rare earths. So all of these do not play well with HF when you get above 1 ppm. Thorium is the worst, but all of them will precipitate at some point. And of course, if they're precipitating, they're stealing HF away from elements that need it. So that's where tungsten and tin come into play. They will start to precipitate when they don't have enough HF attached to them. They'll hydrolyze out of solution. And then silver and lead are in here because they don't play well with HCl. Silver will precipitate and become photosensitive, and lead can precipitate as well, depending on your solubility levels. So that's detailed on this slide, so I'm just going to skip over this. But one other thing to note is that there are other elements that may not precipitate per se, but they'll actually steal the HF away as much as a rare earth would. So our initial desired breakdown for our standards was obviously revolved around matrix. So we wanted to split this into 3 solutions, and then have different calibration ranges for each set. So solution 1, we wanted to be for the nitric elements, the ones that do not care about nitric acid. They're perfectly happy, don't need any other acid to remain stable. And that's a majority of them. Solution 2, we wanted for the ones that required HCl for some reason. And solution 3, we wanted for the ones that require HF. So in our next couple slides, we'll see some of the matrix compatibility issues. So this would be revolving around solution 3. The yellow elements are the ones that we consider HF elements here at IV. And those we wanted to split away from any of the red elements. So we would want the red elements to be in solution 1, but maybe solution 2, if some kind of interference warranted the moving from one to another. And then those peach orange colored ones are the HF thieves. Those are the ones that will actually steal the fluoride away from the yellow elements. So we wanted to kind of keep those away from solution 3 as well. With regards to HCl, as you can see, it's really just the precious metals in the middle in blue. And then only 3 elements don't play well with HCl. Thallium is also in there because you have to worry about the chemical form. Like I mentioned for the barium sulfate, if you use a thallium nitrate that's in the +1 form, it doesn't behave well with HCl. But if you get thallium from a thallium-3 oxide, it actually behaves well in HCl and can be mixed together. I've also pointed out some of these elements in green, like the titanium, zirconium, tin, antimony, and tellurium. We can do those without HF. So we would put those normally in solution 3, but if we identified an interference reason to try to move that to one of the other solutions, we were going to try to accommodate that. So those are the ones that you might see moved around. The last thing we cared about with spectral interferences. How do these things behave on the instruments? So I've got 3 picked out for us to see: cadmium and arsenic, palladium with zirconium and thorium, and finally iridium with yttrium. I wanted to point this one out because if you use yttrium as an internal standard for your method, and you're dealing with precious metals, you're actually eliminating one of your 2 good iridium lines. So I wanted to point out what you might see in that case. So for the cadmium and arsenic, we've known about this interference for a very long time, especially for our trace metals procedure at IV. Cadmium has a line at 228.802, and arsenic is not far, 0.812. So these almost overlap. Depending on the resolution of your instrument, these could be on top of each other. So it's very easy to calibrate for cadmium and completely ignore the fact that arsenic is there. So if we split these apart, we'd be able to get data for a blend that might not have cadmium in it, but has arsenic in it. We'd be able to actually use the 228 line, whereas before it was basically cadmium. Good luck ever trying to see the arsenic because it just wipes it out completely. And in this case, they're not even at equal values. So I have cadmium at 40 ppm and it's a huge peak. Arsenic's at 80 and it's quite small. For the palladium, this one I have 2 interferences. So the zirconium is in red, and it's next to it, but close enough to cause a different kind of issue. So I'm going to draw on here. If you were trying to calibrate on palladium, you might have an interference from the fact that, normally you would want to draw your background point here, and you draw the line, and everything would be fine. But if you have the zirconium in the way, and you don't move it on your instrument software, the line will be drawn near the peak here, and it'll draw a background point like that and take a very different reading from what it should be. And that can skew your results and give you some bias for your samples because your calibration standards aren't done right. In this case, if you use a left point only, you'll have no problems from this. And with the thorium, I wanted to mention that if you have high levels of thorium and you tried to use this line for palladium, you might misinterpret low levels of palladium, even though it's really high levels of thorium. And finally, for iridium and yttrium, this example shows where there's almost complete spectral overlay. So if you're viewing this on the instrument, not as singles, but as a multi, this might look like one, complete line that you'd think is one or the other, but not necessarily both if you're not paying attention to the interference table. So if you combine these at equal levels, you're always going to get a low result if you had both in your calibration standard. So this is what this looks like with iridium and yttrium both at 1 ppm. That's this yellow gold line. It is one peak, but in fact, it's a shoulder peak. So there's really two peaks there, but your instrument's going to think it's one, and you're going to think it's one if you're just looking at it at first glance without running single element standards. So this is where you really have to dig into interferences to understand what's going on. So with respect to interferences, this is, you're not going to have to study this, but this is an example of some of the offline math we use to determine what scheme would minimize the number of major interferences within our standards. So we ran those 40 ppm and 80 ppms single element standards versus our calibration curve and tried to determine, what's causing the interferences. So we said a major interference was going to be anything greater than 5 ppm. So if we ran 80 ppm of the aluminum, does that show up on another line and give us a number that's actually greater than 5 ppm? We would mark it as a problem and try to, solve it by moving some stuff from solution 1, 2, or 3. So we narrowed it down. Playing around with this matrix, we were able to visually see, how many more interferences do we have to deal with, and how can we try to move these around to still keep them chemically stable but minimize those interferences. And as we dug down, this is a smaller table showing only the elements that were, a major problem. And we got 39 major interferences down to only 2. So that was a big deal for trying to optimize these final standards that we come up with. So we took great care in making sure that when we split them up, they were still chemically compatible with the matrix we were going to put them in. So this one is probably the slide everyone's been waiting for. This is our calibration standards. So we've got 3 major sets, the A, B, and C. And then we have that 4th set is just osmium by itself. As Mike stated, we don't do rubidium and osmium very often. And with osmium, there's different safety implications in play. So if we have a day where osmium comes through, it's definitely not every day. It might be once a week or so. We could add this calibration set to, our run and just add an extra 4 standards to the set, and then be able to, get values for osmium too, along with everything. The only thing we have to do is switch out our waste container to an osmium waste container, because we treat that separately from our normal acid waste. So the A standard has everything in nitric acid. Our B standard is a majority of our precious metals, and then some of those HF elements that don't mind being without HF. And then some of those rare earths got put in there because they don't care about HCl either. And then our C standard is HCl, just to help with mercury and palladium stability. We could have done that in nitric, but then we would have had to put palladium and mercury somewhere else. So, all in all, with all the chemical compatibility issues and spectral interferences, this is what we've come to, to believe is the best set of standards for this method. So some other changes and limitations. Some of the wavelengths do go over range at 50 ppm when you're in axial, so we have to switch to radial for that. We still run them in axial in case we have a low level prep. We'd still be able to use the line. But when we switch to radial for those, 393 doesn't go over range anymore. The 455 barium line and then the 670 lithium, they don't go over range, so we're able to use them. Whereas before with our old method, we actually never monitored 670, even though it is a fantastic lithium line. Another thing, the cesium was eliminated as an ionization buffer. So this did limit linearity for potassium, sodium, and lithium, but radial helps with that. Radial mode is more linear, so it really didn't matter that we, excluded it from the method. It was just a different way of doing it. Took us a while to get used to it, but having the dual view helps with that. Of course, this reduced the number of reagents required for the analysis, cuts down on prep time. and also less of a chance of contamination. Every time you pipette something or use a weigh boat, you're introducing the chance of contaminating your samples and altering your analysis for some of those other key elements you're looking for. So that's all for the calibration standards. So Mike's going to move into the next section and talk about managing spectral interferences.
Yeah, thank you, Thomas. So I apologize if you thought we were done talking about spectral interferences, but we are definitely not. Thomas did an excellent job sort of going over how we were keeping in mind spectral interferences while we constructed the calibration curve. But we also need to talk about how do we manage spectral interferences in our samples or your unknowns. So this slide is sort of a classic example that we use in a lot of presentations and just to teach our staff as well. What we have here is a spectra of the sample is a high purity iron sample that we were analyzing at 2,500 ppm iron. And we are looking through and our software says, hey, you've got zinc contamination. So you can see that red spectral, that peak there is lined up with zinc on 206.2 nanometers. So if this is really high purity iron, then maybe we have an issue because we should not see that amount of zinc there. So is this zinc or is it just a spectral interference from the high concentration of iron? So that was our question. So what we decided to do was to spike in 1 ppm of zinc into our high purity iron. So this next spectra shows the red is the same spectra that you saw before, the iron by itself. The blue is the iron with 1 ppm of zinc, and you can see the difference immediately. So the red was all along just a iron spectral interference showing up as zinc. And this sort of speaks to the point of, if you look at the intensities, that blue peak is so much larger. Keep in mind that is only 1 ppm of zinc compared to the red peak. That's iron for that particular line at 2,500 ppm. So some of the things that we could have used all along to help us out, proper peak centering and wavelength calibration is key. But look at those wavelengths on the x-axis there. We're looking at 206.18 to 206.2. So it's a very small window of wavelength nanometers that you're dealing with. So even if you're fully calibrated in range, you might see some issues appear on really close wavelengths like this. So how can you manage these interferences? The first step is your instrument software should have a good library of, relative interferences. So what you should be able to do is, look in your ICP-OES software. There should be a way that you can pull up, hey, what's the possible interferences when I'm looking at this line? And some of them will even tell you, the relative intensity. So like we saw with that zinc, if we were saying, oh, I'm looking for iron in this region, there should be a big zinc interference somewhere right in there. So that's a good source, but it's not the best source because, the software was written when the instrument is brand new. Over time, your instrument's going to reduce in performance. So really the gold standard is running single element standards. Just like we sort of did with the last example, we spiked in zinc on top of it. We could have ran zinc as a single just to see as well. But the single element standards are really the gold standard. So I think coming up next, we have another question for y'all. Do you run any ICP-OES methods that need to account for spectral interferences? And you may or may not know, it might already be built into your method and you're not, not even seeing it day to day. All right. So this is great. Yeah. So most of you are, you do have something that's accounting for these spectral interferences. They are, very important. And then, some of you are not sure as well. Some of you may not need to, depending on your method. Honestly, it really is all based around your method. So let's dig a little bit deeper here on this, dealing with spectral interferences. So, like I said before, running single element standards, especially high purity is key, can allow you to build your own interference table. So what we have here is an example. We collected a lot of data when Thomas was building this new method, and he'd already talked about running single element standards at 40 and 80 ppm. So what we did was we looked back at those single element standards that he ran at 80 ppm, and that's that first column in green. And then we said, okay, well, what does that show up? You know, what does that look like on specific lines for other elements? So in this first example, 80 ppm aluminum shows up as roughly, 0.9, 1 ppm tungsten when you're looking at 220.449 nanometers. So we put this together for all of the single element standards, so all 69 elements, and then all of the lines that we're going to use. And I forget exactly how many lines we're using. It'll be detailed on the next slide, but as you can see, it's a lot of data that we put together. And as you look through this, so the next example is cerium. So next example is cerium. So as you can see, you see a gallium and a palladium interference. But the one I really want to point out is the samarium example. So the second one up from the bottom is samarium. Remember, we were running a single element samarium at 80 ppm. And if you look at that palladium, it's showing up at 121 ppm. So that's a major interference for palladium. Palladium being a precious metal, you'd want to be very cautious if you have samarium around, in your palladium samples, if you're looking at that specific wavelength. So you can take this just as an example and build your own interference table for your method, whatever your method may be. So this is the blue and yellow block is a 2-scale model of what we have done and what we've what I just shown you in the previous slide and what we've done in our lab. So that yellow portion in the top left-hand corner, that's our interference table I just showed you on the previous slide. The interference table we built for our method is the blue block. So again, this is 2-scale, so it was, we actually did more than 69 single elements. We actually looked at others as well, some like the carbon, fluoride, stuff that we don't usually measure on ICP-OES. But we looked at 396 monitored wavelengths. So Thomas did quite a bit of work putting that together. There is a note that Thomas is going to touch on in the next portion. To successfully utilize this method, you need to keep your wavelength calibration up to date. That is key. And you need to have a validated method to keep your peaks centered. And that is also key. And Thomas is going to touch on that when he talks about the validation. So we put all this work into it. The real question is, does it work? And the answer is yes. It works, but it is not a foolproof thing. It's something that you have to use as a tool. So what we have is some results from an ICP-OES run for just a section of analytes, so ruthenium through terbium. And Thomas, if you could mark that gray column for number of lines. Thank you. So what I want you to keep in mind is this is the number of emission lines for those elements that we're looking at. So ruthenium, we're looking at 6. Selenium, we're looking at 4 different emission lines. We count a quote-unquote pass as having a passing result inside of, I believe this one was set for 10% of what the value should be. We change that depending on, what we're looking at. Keep in mind, this is for customs. This is, changing from sample to sample. They can be extreme changes. So when we certify like our stock single element blends, our CGs, we're dealing in, fractions of a percent of from made to value. But as you can see, the left-hand column is not accounting for interferences. So we had one failure of silicon with this sample. So it failed. It had 0% of lines passed. And the best percentage we could get from our made to value was 13.64%. So not great. When you take into account the interference table, silicon passes. About best percent difference was roughly 6.4%. But as you can see, that percentage of passed lines means it only passed on one line. So does that work? In theory, yes, it does. We went back and checked the silicon was actually good in the sample. So that interference table worked. But something to keep in mind too is looking at compare the percentage passed lines from accounting for interferences and not accounting for interferences. Overall, you see a trend that more lines are passing when you account for these interferences. And we only have one example where they decreased, and that is tellurium. So tellurium, you would have to look at, it's a special case. Judging at the fact that it was supposed to be 1 ppm and we don't know what the dilution factor was on this, it's probably based on concentration. Tellurium is not a very intense spectra. So my guess would be it's something that we would want to look at, but it's probably based around concentration. So as you can see, it's a very beneficial tool, but it's not it's not black and white. You do still need to look at all the data, but it gives you more information to use while you're looking at the data. And I'm going to pass it back over to Thomas.
All right, thanks, Mike. Our last topic is validating the method. So obviously, we built it from the ground up with new calibration standards and a new interference table. So how do we pull all this together and make sure it is fit for our purpose? So we're going to go through 4 different validation concerns. First is the stability of calibration standards. The next is the calibration verification. How do we know that the calibration curve is actually valid? And then next, at IV, we've always worried about matrix matching our standards versus our samples. So how important is that with this new method? And then finally, what instrument setup do we have to use in order to make sure all of our elements work? So first is the stability of the calibration standards. The highest concentration versions of these 3 sets have been entered into our stability testing program. So we do have concentrates that we make these from. So those highest levels that we have are being monitored for stability, and we are making the assumption that the lower level ones are stable over time. But we'll do calibration verification checks to make sure the stability is still good, even for the diluted samples. We have collected 18 months of stability data so far, and we'll continue to collect data on these for at least 5 years, even though at this point we don't expect to identify instability. Basically, if it works past 6 months, it's generally not going to have a stability problem unless it's a really strange problem. So from here, we'll go into calibration verification. As we stated before, we're using the Agilent 5110 dual view instrument. And we've noticed that Axial is not always linear. You always think that the ICP method on OES is a linear method. It's not actually the case when you start going into higher levels of concentration. So we started to evaluate the parabolic rational function, which their software dubs as the rational method. There is a really good white paper on this subject from Agilent. It was originally published in 1977 when it was Varian, and it revolves around the AA systems. But this scheme seems to work for the Axial systems that our Agilent system has. So it might not necessarily work for other types of optical systems. I know Spectral uses a different optical system, so you might have to look around and see if it's not linear, a different model is probably going to come into play. But for our purposes, we stuck with the rational method, and it gave a better calibration equation for all elements. So we chose it for the final validation activities. So this is a graph showing really what's going on with our calibration curves. This is aluminum 167. It seems to be the line with the absolute worst curvature, and this is actually in radial. Axial looks way worse. So from this example, you can see we go from 0 ppm through the 50 ppm point, which is down here, but we actually expanded this curve all the way to 500 ppm. And as you can see, there's some massive curvature that deviates from a linear regression. So it was actually so bad when you said, and I want to use a linear fit, it didn't calibrate. It wouldn't even give me a formula. So as I removed those higher calibration ranges, I couldn't get a linear model to work until I got to 50 ppm. So it would work at 50 ppm. I got a linear fit, and that's what the green line is. As you can see, the error starts to deviate after 50 ppm. Even 50 has a little bit of a deviation here, but this gap gets bigger, this gap gets bigger, and now we've got a huge deviation, and this one doesn't even reach on the curve that I have shown. So that's obviously a concern for when you're running samples. Hey, am I getting the right result? But in this case, when we switched to rational, we really were. So we would test the single element standards, some multi-element standards with this rational curve to make sure they landed where we expected them to. And this model works very well. We noticed that Axial benefited a lot from this method, but some of the radial wavelengths did too. But overall, the radials really were linear, and that just has to do with viewing the side of the plasma instead of looking through the cone of the plasma. Makes a big difference in the light that your instrument will see. So next, peak centering and backgrounds. Mike mentioned that this is critical. The peak positions are locked down in our template, so they never get changed. Their software package comes with a peak drift feature. So it's called the peak. You select the peak track lines. It's built into the software. It monitors the carbon 192 and 5 different argon lines that are in the whole dynamic range of the spectra, all the way to 700 nanometers. So you get something that's always present, whether you're aspirating a solution or not. It will see these carbon and argon lines, and it knows where they should be. And if it shifts a little bit, it'll shift all of your peaks to compensate. And that makes it so you don't have to recenter peaks in your worksheet, which is huge in order to make the interference table work properly. The next thing is the background. So your background has a fitted model that works very well, but sometimes that messes up when you've got those interference shoulder peaks. It'll start drawing some weird backgrounds. So some of those get changed to right adjusted, left adjusted, or both 2-point background. Whatever we picked, we locked it down. So that makes it so that the interference table doesn't change, because those are based on those peaks being centered and those specific background points being utilized. If you make a change to that, you'll have to revalidate your method. So that's why we locked them down in a template. Always use the same template when we do a new run, and the interference table section of our processing sheet is valid. Next is detection limits and LOQs. So obviously, this is something that always has to be mentioned when you're dealing with calibration curves. Detection limits, of course, depend on the element and the wavelength. So you might have a really good cadmium line and a really bad cadmium line. They both work just as well at high levels, but then you might have a different, detection limit for it because it's just not as intense. So that just depends on which wavelength you're looking at. But a detection limit's defined as 3 times the standard deviation of your blanks, and the limit of quantification, or your LOQ, is 10 times the standard deviation of your blanks. And I will say that this is a much better limit if you're looking for reliable measurements. So we've got another slide that shows what our limits for this, what these limits are. But those limits are helping determine what dilution factor to use in our samples when we have varying concentration levels. Because my complicated blend example from before had a pretty big range, but I'll tell you what, with the customs that we make for some of the folks out there, it can be an even bigger range. So these limits make it so that we can do less preps in order to test these custom solutions without too much heartache. So this is our table of basically LOQs and the maximum limits allowed on the method. So this is IV's sample prep logic. So we would prep most of our elements to match our mid standard. So of course, on our previous periodic table slide, we showed that our low standard is 0.5 ppm, our mid standard is 5, and our high standard is 50. We want to go into the middle. It's in the linear range because, like I said, most of them were pretty linear on the low end, and you get the curvature on the high end. So if you put it at 5, you're also matching one of the standards. You just get more reliable results on that. Now, if you have a blend with differing concentration levels, that's where some of this logic has to come into play. So we'll like to prep high elements to match the ideal max. So the ideal max, again, is matching one of the standards we're actually testing. But sometimes that doesn't make everything fall within our min. So we can go beyond and go to 80 ppm because that's what I validated the method with those single element standards and said, oh, 80 still fits on the curve. Believe it or not, some of these elements work really well. They're linear enough. The rational curve really is valid beyond. I had a silicon example where we ran it at 250 ppm and it was spot on, even though the calibration range was 50. It actually passed with a very small error. So again, it does depend on what you validate though, because your auditors will care about that. But with respect to going high, you also have to make sure it's good on the low end. So you might have high elements and then low elements that might not fall within your ideal min. It's where you have to come in with a second prep. So Mike mentioned, 1.5 preps per sample was our average. We cut it down, but they do still exist. It did not go to 1 prep. But again, this improved the method a lot. Now, can't stress this enough though. Don't go beyond what you validate. You'll have to jump through a lot of hoops in order to prove what you're testing is actually valid. So keep that in mind. So now I've got another question for you. I think this is our last question of the day. Does your method have specified minimum and maximum level prepping requirements to fall within your validated calibration range? That's similar to the table I just showed. All right. And it looks like the overwhelming yes on this one. So a majority of you do have, specified limits, which is to be expected. It's definitely a requirement of EPA and many other accrediting bodies. So that makes sense. All right. And then our one of our last ones, matrix matching concerns. So with validating, we were concerned, we had different matrices for our calibration standards. But we weren't sure, at first, does that matter? Are we going to create a bias by having a different matrix? The overall answer was no. We actually didn't see much bias. So we switched samples from nitric to HCl, and we tested this in a variety of ways. Didn't seem to change the signal intensity at all. So prepping samples in 10% HCl instead of 5% doesn't make any changes in the signal intensity. So that's good. But I will say that sometimes we do have to prep in 10%, even though our standards are in 5, to help enhance the stability of low-level silver. Silver will precipitate as the chloride and become photosensitive. So if you prep it to a low enough value and then throw HCl at it, it'll actually stay in solution. So that's a strategy we use. If we have silver mixed with other precious metals or the blend just happens to be an HCl, we'll make sure the silver gets prepped lower than normal. Instead of our ideal 5, we'll go up to 1 ppm and stay on the low end. Put it in 10% HCl and everything works very well. Another thing to note was with respect to matrix, radial mode was less affected by changes in matrix. And obviously that's due to the fact that you're looking at the side of the plasma instead of head on. It's just less susceptible to matrix interferences. The biggest problem we do have with matrix, though, is really high total dissolved solids, or TDS. That's really what causes the most signal quenching, and radial view helps with that. Sometimes you can't get around that because you have very high levels of maybe iron or something and low levels of some of the other transition metals. If you want to see the low levels, you can only dilute so much before you go below the LOQ, so that high iron will start to mess with your signal. And there's just nothing you can do to get around that. The last thing for validation is instrument setup. So we had to specify, what intro system do we use on our ICP in order to get reliable results. So we utilize the HF resistance system to help mitigate silicon and boron contamination. Obviously, we're testing every element you can. So silicon and boron are just as important as all the others. So we have to avoid the glass system. So we've got a PTFE cyclonic spray chamber, a peak concentric nebulizer, a fully demountable torch equipped with an alumina injector, and a ceramic outer tube. I will note that you can use a sapphire injector. We just found that for this method, we didn't need to go to the extra high purity alumina. So the lower grade alumina was just fine. But when we did try to switch to a ceramic injector that kind of matches the ceramic outer tube, we had issues with silicon. So again, it depends on what elements you care about. If you're not caring about boron and silicon, glass will work unless you've got HF involved. You'll just introduce some other interferences that might give you some headache in the end. With respect to the rinse regimen, we do have some global rinses. At the start of our runs, we'll run nitric and HCl to make sure the system is clean before running our standards. And at the end of the run, it will run, like I said, it runs through the night. So at the end, it'll run nitric, HCl, but then it'll also run a 2.5% solution of RBS 25. That's a surfactant based solution that's basic. That works really well for reconditioning the spray chamber. Even if it's glass or PTFE, that works really well to keep it wetting properly so that you can do less hardcore maintenance offline. But that works best if you do a final rinse of water. So I think we have like 6 water samples at the end of the run and then another 10-minute final rinse. Between samples, that's our method rinse. We usually use 1% nitric, and we'll swap with 1% HCl if we're running osmium. Obviously, that helps with the memory interferences of osmium. If it touches any amount of nitric, it will stick to the plastic like crazy. Obviously, a bigger concern with mass spec, but you can see it on OES as well, even though the detection limits aren't nearly as good as mass spec. Another strategy we do use for rinsing, we do insert dummy samples. So the technicians will insert blanks after some of those high TDS samples that you can't get around because it's got high elements and low elements. So sometimes they'll run one or even several blanks after a high level solution to make sure that when the next actual sample gets run, it's not contaminated by that previous sample, because memory interferences are still a concern. And if you don't, take proper care with rinses, you can still run into some problems. So I'm going to pass it back to Mike to close us out with the benefits of this method.
Yep. Thank you, Thomas. So as you can see, we sort of threw a lot of information at you, but I wanted to close it out with, what did we see? Did we hit the items on our most wanted improvement list? And the answer is yes. So from everything that we presented, I think you can see that this is a very robust method. Not a lot of spectral interferences. We have ways to account for them if we do encounter them in our samples. We've done a lot of testing to make sure that the matrix matching is okay, that we've got a good validated calibration range. So overall, it's a very robust method. Did we save any time? Yes. We have ran the numbers and we cut down the number of preps per sample from 1.5 to 1.1. And also just sort of talking to our QC technicians and monitoring the time they spend prepping. What used to take them 3 minutes per prep is now taking them about 2 minutes per prep. So we've really saved a lot of time with this new method. And one of the things that our staff has really enjoyed is the reduction of what we call second checks, or, as Thomas mentioned, this method would run overnight. In the morning, they would come in and check their results. If anything failed, they would need to go in and recheck that blend to make sure it passed, either running it on a different instrument, re-prepping it to a different dilution factor. It was very rare for us to have days where there would be no second checks. They would happen maybe once every 4 or 5 months. Now we're seeing it a couple times a month. So that's been a great improvement as well. So are there any downsides? Don't want to, sugarcoat everything. There is one downside, but it is limited. Our technicians need to know this method inside and out. So they need to know what their, calibrated range is. They need to know the matrix. Whereas before, our old method, you threw it in 10% HCl, you spiked in cesium, that was it. With this one, our technicians really need to be aware of what they're looking for and how to prep it. Other than that, we haven't come across any other downsides. And after our technicians have been trained, they are very excited about switching to this new method. So as you can imagine, making changes in the lab, sometimes you deal with a lot of hesitancy. This one, as soon as they got a chance to run it, everyone flipped over to this new method almost instantly. So that was great. But you don't have to take my word for it. We do have the most concentrated versions of these calibration curve standards. We've been calling them MEB 4A, 4B, and 4C. If you would like to try them, please contact us and ask for these IV lot numbers, or these IV solution numbers, I should say. And if you're looking for osmium, again, osmium is all by itself, so that's just our custom grade osmium. It's the highest, it's the most accurate osmium standard that we have on the market, and we're making improvements to it even now. So if there are any other questions just to close this thing out, you can always visit us online at inorganicventures.com. There's a ton of resources there. There's a nice technical forum. You can also contact us directly. We have a great technical support team that would be happy to answer any of your questions, customer or not. So with that, I want to thank everyone for their time, and we would love to answer any questions that you may have. So please feel free to ask.
All right, Mike, Thomas, thank you for the extremely interesting and in-depth conversation regarding ICP calibration and interferences and things of that nature. So it looks like we've got a few questions already lined up in the queue. So I'll just jump right in. And I'm going to go ahead and apologize in advance if I say anybody's name incorrectly. That certainly wasn't my intention. Our first one is from Karis. Can you please explain the benefits and disadvantages of using a cesium ionization buffer, for example, in something like a lithium borate digestion?
Sure. One of the benefits of using the cesium buffer is to help with, basically, if you were testing for lithium, it would help with that, but it's going to help with your potassium and your sodium, mainly with axial view. So with axial view, you get some interferences, some matrix suppression that doesn't really behave because of the amount of TDS in your samples versus your standards. So what we've noticed is when you added the cesium buffer to your samples and your standards, it normalized that for the lithium, potassium, and sodium. So if you're using a lithium borate digestion, obviously you're not looking for lithium, but this would help with your potassium and sodium. If you cared about those numbers, your standards are likely not to have the same amount of lithium borate in them, so they wouldn't truly be matrix matched. The cesium would help normalize that and gives you results that are much closer than if you didn't have the lithium borate.
Cool. Thank you for that, Thomas. So just kind of continuing the conversation with cesium, we've got a question from Jake. And when you decided to cut the step of adding cesium to each sample and standard, did you consider adding the ionization buffer in line using a T in the introduction system? That way the samples and standard receive the same amount of cesium and the tech is only prepping one ionization buffer or internal standard bottle.
Yeah, I can answer that. Yeah, we have thought about that in the past, and we didn't really go into it in this presentation. But part of the old method was we also had prepared pre-mixed 10% HCl that was already spiked with 500 ppm cesium. The issue that we would run into is, Thomas briefly mentioned it, when talking about the insoluble platinum cesium chloride molecule that would drop out. So on occasion, we would have samples that we would have to not add cesium to. So that was always on our technicians' minds. And also, one of the liabilities of having it pre-mixed was the dilution factor. So if there was something that needed like a 2x dilution, if you're diluting only 2 times, you're only getting 250 ppm cesium instead of 500. But adding it in through a T would be a good way to do it if we didn't have to account for those ones where we had to leave out the cesium spike.
One other thing I wanted to mention, I've been told not to mention it too much, but I mean, we make high purity standards. That's what we're in the business of doing. But I will say, we provide trace metals data for all of our solutions. Not everything is 99.9999% pure. So one of the things you need to keep in mind when you're adding any reagent is it clean enough for what you're testing? So one of the things we have come across before, it's very rare, but if you have high levels of something, but then you have low levels of some of those alkalis or alkaline earths, you might have some issues when you add that cesium because you're really adding a little bit of contamination that would actually bias your results and can cause you some headache that you're not really sure where it's coming from. It could be coming from your cesium buffer or maybe your nitric acid or your HCl. So that's one of the reasons I also wanted to eliminate the cesium. It was just an extra reagent that might contribute a bias in those low level majors.
Excellent, guys. Excellent. Okay. I do have a couple of comments here from Goran. I want to make sure I didn't misunderstand what you were saying, Goran. So it looks like you have some comments concerning splitting the calibration and some another comment on sodium and lithium. But if you have a sort of a question or something you want us to comment on, Goran, feel free to throw that into the question and answer section. I'm going to move on to the next one that came in from one of our other attendees. And can you just speak more to how you're using this interference table that you all presented? And is this something within your software or in the software?
Sure. So yeah, I can tackle some of that, and Mike might have some stuff to add. But our interference table is in Excel. So we have built a model based on a calibration curve, and then running those single element standards. We mined the data of all the results on different lines for like we tested the aluminum. We saw if it interfered on other elements, and we would report that. And we're testing known samples. So our samples, we know what's in it. So we might test something with calcium, mag, potassium, sodium. We throw that into our interference table as, hey, we know these are in here. What is our new expected value for other things that might be present based on the interferences we expect to see? So this is done in a spreadsheet that's not in the Agilent software because that's kind of a black box, so to speak. We're just using offline data and making a new basically prediction of what to expect to see. We know there should be like 1,000 ppm calcium, but with interferences, our software is probably going to tell us it's 1,100. So then our new comparison value is 1,100 when we account for interferences. So that's something that the software doesn't do, but we're doing offline in Excel. But I don't know if Mike, you wanted to add anything to that.
Yeah, I would say that's an excellent answer. Yeah, we do a lot of our workup offline in our own spreadsheets because what Thomas had mentioned, it is a black box, but it's also every sample is getting monitored at close to 400 different lines. So it's a lot of data to crunch together. And we found that, making our own Excel spreadsheets that we can just take the raw data file and plug into, we can, create the Excel file to show us, like Thomas said, we know what we're expecting to see. So we see the results for only the lines, only the elements that we're expecting to look at. And we have some safety protocols built in as well. So if we see signal on something that shouldn't be there, it will tell us, it'll say, hey, calcium's not supposed to be here, but you need to look at calcium because you're getting signal on, the majority of these lines and they're all lining up. So yeah, we do a lot of work offline, off the instrument software in Excel.
Great. Okay. Thanks, guys, for that. All right. So we've got another question here from Ravinder. Uh, so there are a number of ICP-OES instrument companies that offer wavelength calibration standards. Can you comment on the basis of the element selection in these standards?
Yeah, so that really depends on the actual instrument manufacturer. So they are coming up with their own strategies within their software to say, hey, we're going to calibrate um, our wavelength. So that's basically our peak centering of the instrument in the full range of spectra from 160 nanometers or even lower, all the way through 760, the lithium on the high end. And again, it might go a little bit farther for certain lines. But you want to make sure that each one of those calibration ranges, is good. They have every instrument is different. Some of them have one detector that's split up by that Axial grading, like the Agilent does. But Spectro has a different way of doing it. They actually have different CCDs that are done through, I guess, a prism system. So they actually have different detectors that do certain ranges. So I think the strategy that those companies take is to make sure that each one of those detectors is properly centered, because their softwares and instrument, the hardware of those things are done differently. So they choose the elements that land on each one of those consistently, but also the ones that probably have strong signal. So you wouldn't typically use something like tellurium very often for that, but some of them use, I think sulfur is in there because it's on the low end. Lithium is sometimes in there because it's on the high end, but I think it's usually wavelength dependent. But sometimes it's matrix dependent as well. So they try to avoid using silver because they know it'll precipitate. They try to avoid some of those rare earths for the same reason.
And I'll jump in as well, Thomas. A key with those wavelength calibration standards is purity as well, because if you do have something in there that shouldn't be, it can throw that wavelength calibration off. But Thomas is absolutely right. It's more about not necessarily the element, but the emission wavelengths of those elements that really matter. And it's really up to the instrument manufacturer, because they have designed the hardware so they know exactly what emission wavelengths they're looking for when the instrument performs a wavelength calibration.
All right. Thanks, guys. Good question. Great answers. All right. So we're going to kind of move along here. And Christian looks like he's working with samples of geothermal waters and solving, and he would like to ask about solving interferences in these samples. And he follows up and says the main problem is that he's trying to measure low concentrations of aluminum and magnesium and high concentrations of sodium in the same sample. Can you guys comment on that?
Well, I think the main thing you're going to have trouble with is the higher level of sodium is going to give you some signal depression. So one of the things you'll probably want to do is truly matrix match that. So any of your standards, you'll want to spike in the same amount of sodium in order to get a good signal response. Alternatively, you could do a standard addition method and basically do a spike recovery for the aluminum and magnesium, and that would probably work best. Sodium is what's going to cause you the trouble with that. Cesium buffer shouldn't help with those two elements, so I would go with an internal standard matrix matching, or the spike recovery.
All right. Thanks for that, Thomas. We have a question from Jacob, and it looks like this might be our last one. Looks like he didn't catch the full significance of the rubidium and osmium additions. Are these now in lieu of cesium, or what is the reason that we were adding these in?
Yeah, I can jump in with that one. So the rubidium and osmium, our old method did not have them as part of the calibration. So any samples that would contain cesium, rubidium, or osmium, we wouldn't be able to run with the rest of the samples to essentially check those three elements. Cesium, again, we didn't put in a new method just because wavelength intensity is not great. So cesiums are still being checked on ICP mass spec. But if it's rubidium, we can now successfully put it in our method and not have to worry about a second check after everything else is passed to say, okay, got everything. Now I need to check off this rubidium to clear this blend and make sure it's good. Same thing for osmium. The old method, osmium was not there. To do so, we would have to run a completely separate method. Part of the reason is, a safety concern of how we handle the waste. But with this new one, we just simply tack on the extra standards, change out the waste, change out the method rent solution, and it is good to go. So it's a lot of basically just cutting down the work for our technicians, where they don't have to go in and repeat work on the same blend. Hopefully they can do one test and get the whole blend checked off.
And one other thing I'll comment on that, as Mike mentioned, cesium has terrible intensity. It's actually really bad on an OES. I mean, the detection limit on that is 100 ppm instead of sub ppm levels. Rubidium is not far behind, but our old instrument didn't have a rubidium line, but our new one does. That actually works really well. So that's on the high end. It's actually, rubidium shows up on one of our instruments and not the others. So that was something we took advantage with the new Agilent system, is a rubidium line that we didn't have access to before. So we were able to add that with a decent detection limit, but still not great. So if you looked at one of the previous slides with the ideal value for that, rubidium is higher, but it does work. So we were excited to be able to add that. But both of those are routinely checked on a mass spec with absolutely no problems. We just like to have our workhorse be an OES.
Okay. All right. It looks like, yeah, good questions. They're like potato chips. You just can't have enough, right? We got one from Jessica coming in. Can I have silicon in the same standard together with other elements such as iron, sodium, potassium, manganese, vanadium, calcium, things of that nature? What do you guys think?
Absolutely. It just depends on the concentration level. So silicon is one of those HF elements, and obviously it will give you issues with potassium if it's too high, but it'll also give issues with calcium because of the HF content. Iron doesn't care, manganese doesn't care, and vanadium won't care. So those you don't have to worry about. So your stability on this is going to revolve around calcium and potassium. Silicon doesn't actually need HF until you get to 10 ppm. So anything above 10 ppm needs a level of HF to remain stable. And if you put in too much HF, you'll precipitate calcium. But we have noticed that the gel issue that I mentioned before is really silicon and potassium at levels above 200 ppm. So I with reasonable confidence, I can say if you wanted all these elements at 100 ppm or lower, you'll have no problems.
All right. And that looks like we've come to the end of our questions. So guys, I just want to say thank you. Thank you for the presentation. Thank you for the information. To all the attendees, we appreciate you stopping by and talking with us and having the conversation with us this morning. And I also want to thank Brian for the introductions he did earlier, and also thank Maddie for helping us out through the putting together all the details of the presentation and the talk today. So once again, on behalf of Inorganic Ventures, everybody, thank you, and we hope you have a good day. If you have any other questions, always feel free to reach out to us at either info@inorganic.com or through your customer experience reps that you work through. Thank you.
Thank you all.
Thank you.